Have you ever stood in a line at a coffee shop, wondering why it takes so long to get your latte? Or maybe you have been stuck in traffic, frustrated by endless wait at a signal. Or you have waited on hold with customer service, questioning if anyone is actually working on the other end. Well, guess what? There is a branch of mathematics that studies problems just like these. It's called queuing theory. And it's the key to understanding how to optimize lines, wait times, and system across industries. Today we are diving into the fascinating world of queuing theory. An introduction to a series where we explore this incredible subject step by step. Stick around, because by the end of this video, you will see the hidden patterns in the lines and delays everywhere you go. Let's start with a few questions. How can a hospital reduce wait times in its emergency room? What's the best way to design a toll booth system to minimize traffic jams? And how can big logistic companies optimize their logistics to deliver package faster? Queuing theory is the science of waiting lines. It combines maths, probability, and logic to analyze system where people or tasks wait for service. These systems are everywhere: banks, supermarkets, airports, and even your internet connection. How does it work? Let's break it down. Every queue has three basic components: arrival of the customers or task, the service process, and the queue itself. Let's imagine a town called Queville. Queville has one drug rehab center. Queville Rehab Center receives one patient per day on an average. Each patient requires 28 days to recover. And the rehab have 30 beds for patient. In queuing theory, it can be called as MM30 model. Let's understand what does it mean. This is a candles notation which have 5 sections: A, B, C, K and D, where A is for arrival rate, B is for service rate, C is for number of servers, K is for maximum capacity of system, and D is for queue discipline. It is assumed to be first come, first serve if not otherwise stated. In our problem, first M stand for Markovian arrival rate. Arrival rate or service rate can have different distribution. First is Markovian, which is like Poisson distribution or exponential distribution. Second, deterministic, and third, general. We will learn about these distributions and their amazing properties in subsequent videos. So we used queuing theory to calculate how many patients get admitted without waiting, how long patients wait on an average, and how many patients are in the line at a given time. To answer these questions, first we calculate utilization, which tells us how busy the hospital is. Utilization factor is denoted by rho, and the formula for rho is lambda by mu. That gives us 0.9333 as the answer. This means the hospital is busy 93.33% of the time. Next, we calculated the average number of patients waiting for the beds. For this, we calculated LQ. And the formula is LQ is equal to rho squared divided by 1 minus rho, which comes out to 14.77. or approximately 15 patients waiting for beds. Finally, we found out how long each patient wait. In this, we use Little's formula. On an average, the patient wait 15 days for a bed. That's too long. Now the question is, if we combine 3 rehab centers where the patient can move from one rehab to another freely and each rehab have same arrival rate of 1 patient per day, service rate of 1 by 28 patient per day, and the number of beds 30, does it improve our system or does the system remain same? Write us in comments and we will discuss about this in our next video on queuing theory. Queues are everywhere, and with queuing theory you can turn them into opportunities for improvement. So hit that like button, subscribe our channel and join us in our journey into the science of waiting lines. Next up in the series, the simplest queuing model and why it is more powerful than you think. Don't miss it.